Welcome to lecture number 6 of Digital Signal Processing. In this lecture, we will discuss useful models of discrete time domain and then learn manipulation techniques of continuous time signal. Then we will move towards the manipulation technique of discrete time signals. Now moving towards discrete time domain. So those two models we have discussed in continuous time domain also exist in discrete time domain. The first model is discrete time unit step function. The discrete time counterpart of the unit step function u of t is now u of n. There we studied u of t, and because we are here talking about discrete time, so the function is u of n, and u of n can be defined as u of n is equal to 1 for all samples n greater than and equals to 0, and u of n is equal to 0 for all samples before n is equal to 0. Second plot is basically the application of unit step function similar to that we have discussed in continuous time domain. That is, if we want to start a signal at n is equal to 0 so that it has 0 values for n less than 0, what we have to do, we need only multiply the signal by u of n. This is very similar to the discussion we have done for continuous time domain. So same is valid in discrete time domain. If we want to convert a signal into a causal signal, or if we want to start the signal for n greater than and equals to 0, what we have to do? We have to just multiply that signal with u of n. So we get a causal signal in result. Now moving towards the second important model of discrete time domain, which is discrete time impulse function. It is denoted by sigma of n. It is the counterpart of the continuous time impulse function, which was sigma of t, which we discussed in the previous slides. So the mathematical definition of this discrete time impulse function is sigma of n is equal to 1 for n is equal to 0, and sigma of n is equal to 0 for n not equals to 0. The unit impulse sequence in discrete time domain is very much simpler as compared to the continuous time domain. As we do not have any rectangular pulse model here, when we discussed the continuous time impulse function, recall that we have discussed about the rectangular pulse of width nearly equals to 0 and height nearly equals to infinite. But there is no such height and width matters here. Just we have a very simple function which exists for n for only one sample, and the number of that sample is n is equal to 0. For n is equal to 1, 2, 3 and so on, and similarly for negative side -1, -2, -3 and so on, we have the function value or the sample values equal to 0. only at single sample this function exists, and that value of a sample is 0, and the value of function at that sample is 1. As you can see from the plot also, we have a very simple unit impulse sequence. In the second plot, you can see there is a shifted impulse sequence. How we can shift a sequence or signal, we will learn it in the later slides. But for simplicity, here we are assuming that we can shift or slide this impulse signal as well. As far as application of this impulse function is concerned, there are various applications of this impulse sequence. This impulse sequence is mainly building block of convolution integral or convolution sum 2, which will be discussed in the later lectures. But for here, you must learn the basic sequence of this impulse, which is very simple as shown in the plot. So moving towards the next topic, which is manipulation of continuous time signal. Actually, we are more interested in discussing the manipulation of discrete time signals. But for your convenience and easiness, I will discuss continuous time domain manipulation first, then we will shift our focus towards the discrete time signals. So the first manipulation technique of continuous time signal is time shifting. Basically, there are three useful signal manipulation techniques. First one is shifting. In generally, we can say shifting. Second one, in general, we can say scaling. And the third one is inversion. So since the independent variable in our signal description is time, so we are referring this technique as time shifting, time scaling, and time inversion. However, we can limit or our discussion to the functions having time variable or n, which is sequence for discrete time signals. Another discussion for this shifting, scaling, and inversion operation can be for the variable frequency or distance, which is other than time and sample sequence. But as we are interested more in continuous time signal and discrete time signal, so our focus will be on time shifting, time scaling, and time reversal, and then we will move towards sequence shifting, sequence scaling, and sequence reversal. Now we are trying to understand the concept of time shifting with the help of an example. So as shown in this slide, there are three plots. The first plot is for the signal x of t. It is basically a generic signal. Second plot is the same signal delayed by t second, capital T second. So we will denote this second plot by phi of t. So first signal is denoted by x of t and the second signal is denoted by phi of t, which is actually the same signal but delayed or shifted by t second, capital T second. Or in other words, we can say whatever happens in the first signal, which is x of t, at some time instant also happens in the second signal, which is phi of t, capital T second time later. That is what happens at with the first signal, or the same scenario is going to happen with the second signal, but with some time delay, that is capital T. So the actual signal is x of t, and the second signal, which is the delayed version of the original signal, is x of t minus capital T. So in short, what we are doing, we are time shifting a signal by capital T. So we are replacing the index small t with t minus capital T. As you can see in the figure 2, that t is replaced by t minus capital T. If capital T is positive here, it means that the signal is shifted to the right, or in other words we can say that the signal is delayed. But if capital T is negative, then the shift of the signal will be to the left, and we will say that this signal is the advanced version of the original signal. We have two terminologies, time delay or time advance. If capital T is positive, then the signal is time delayed signal, and if the capital T is negative, then the so for example, if we have a signal x of t and there is another signal which is x of t minus 2, then what will you comment? This signal is time delayed or time advanced? I am repeating my question, that if we have an original signal which is denoted by x of t, and if we have another signal x of t minus 2, then x of t minus 2 is the advanced version of the original signal or the delayed version of the original signal. So now we look at the time of capital T, and here it is positive. So the signal is delayed version of the original signal. And how much delay? Delay is equal to the 2 seconds. Now we will learn this concept with the help of an example which is in the upcoming slide. So the task related to this topic is shown in your slide. Task is an exponential function x of t is equal to exponential e raised to power minus 2t, as shown in the figure, is delayed by 1 second. What you have to do is sketch the delayed function. This is the original function, and you have to plot the delayed function. And the second part of this question is repeat the same problem with x of t advanced by 1 second. I hope that question is quite easy and you all will solve it without any difficulty. Question is so easy, you can try at your own. Original signal is shown in the slide, and what you have to do, you have to perform two operations. First, you have to plot the delayed function, and second, you have to plot the advanced function. Take your time to solve this task. If anyone has any query, he may discuss it in the live session, but I think that the question is quite easy. So now moving towards the next topic, which is time scaling. The compression or expansion of a signal in time is known as time scaling. Suppose you have a signal x of t as shown in the figure A, another signal phi of t, which is the compressed version of x of t, and it is compressed by the factor of 2. Therefore, what is happening in the original signal in figure A, that is x of t, at any time instant t, also happens to the second signal phi of t, but the time instant will be t minus 2. Using the same argument, we can also comment that the original signal x of t, as in figure A, can be expanded, or in other words can be slowed down in time by a factor of 2. We are taking 2 as an example, and the resultant plot will be as shown in figure C. So the figure C shows x of t by 2, which is the original signal x of t expanded in time by a factor of 2. Another thing you can observe in this time scaling operation is that the origin, which is t is equal to 0, is the anchor point, and it remains unchanged under the scaling operation. Or summarizing our discussion regarding time scaling, if we want to time scale any signal by a factor a, suppose we want to time scale any signal with the factor of a, what we have to do? We have to replace t, variable t, which is time, with at. So we have a choice for variable a. We can have value of a greater than 1 also and less than 1 also. If a is greater than 1, then the scaling results in compression, and if a is less than 1, the scaling results in expansion of the signal. You can verify this statement from these three plots also. First signal is x of t, second signal is x of at, and here a is equal to 2, which is greater than 1, and the resultant signal is the compressed version. And in the third figure, a is equal to 1 upon 2, that is 0.5, and here a is less than 1, so the scaling results in expansion. To understand the concept of time scaling and for your practice, there is a task. You have a plot as shown in the figure x of t. You have to sketch this time signal compressed by a factor of t. Then you have to repeat the same problem for the same signal expanded by the factor of 2. So here the numerical will be of compression and expansion both, In one statement or in one part you have to time compressed the signal by a factor of 3, and in the second part you will time expand the signal by a factor of 2. I hope this task is very easy and you can do it easily. If you have any query or problem regarding this solving this question, you may discuss it with me in the live session. But I hope the question is quite easy and you will not having any difficulty in plotting the sketch. Just take care of the values of time. You have already given the function 2 raised to power minus e raised to power 2 into e raised to power minus t by 2. Function is written in the slide, and this function exists for 0 to 3, and from minus 1.5 till 0 the function is 2. The third manipulation technique of continuous time signal is time reversal. Consider the signal x of t as shown in the figure A. We can view this signal x of t as a rigid wireframe anchored at the vertical axis. Now to reverse or to time reverse this signal, what we have to do, we only rotate this frame 180 degree about the vertical axis. So just simple rotation about the vertical axis, and how much degree rotation? Exactly 180. So this time reversal, or we can say the reflection of the original signal x of t about the vertical axis, gives us the second signal, which is phi of t as shown in the second figure B. You may also observe that whatever happens in the first plot at some time instant t also going to happen at the time instant minus t in the second plot. So we can say that second plot, which is phi of t, is equal to x of minus t. So to time reverse a signal, we just replace the time variable t with minus t, and the time reversal of signal x of t results in a signal x of minus t. Please remember that this reversal is performed about the vertical axis because we are treating this axis as an anchor point. If we rotate or perform the reversal along the horizontal axis, then we will not get x of minus t. We will get another signal which is minus x of t. So remember that for time reversal we have to rotate the signal along the vertical axis. If we rotate the signal along the horizontal axis, then we get minus x of t, which is not the time reversed signal. Time reversed signal is x of minus t. So a task for time reversal, you have a signal x of t and you just have to plot the x of minus t. I hope that this task is very much easy. But again, if you have any query regarding solving this question, you may discuss it with me in the live session. But I hope that this task is very easy and you will not face any difficulty while solving it. signal operations for shifting, scaling, and reversal as discussed for continuous time signals in the previous slides also apply to discrete time signals, but with some modification. So the first is shifting. Here we are not saying the time shifting because we have a sequence. So we are generally saying shifting, operation or shifting of a sequence. So consider a signal as shown in figure A, and we are labeling this signal as x of n, and we are delaying as we know that what is the delay is, and what is the advancement in function is, as we have completed it in the continuous time domain. So I am just delaying this signal by 5 units, or I can say I am delaying this signal or right shifting this signal by 5 units. So I will obtain the second plot. So if I want to shift a sequence by, for example, m samples or m units, here m must be an integer because we are talking about the sequence. So if we want to shift the sequence by m integer or m units or m samples, we just replace the n with n minus m. The argument of x is n. So we just replace x of n with x of n minus m, and that x of n minus m actually represent the shifted signal x of n, and how much the shifting is by m units. So similar like in continuous time domain we have positive value of capital T and negative value of capital T. Here also we can comment that we can have positive value of capital M and negative value of capital M. So if we have the positive value of capital M, then this sequence is shifted to the right, or we can say that the sequence is delayed. Or if the m is negative, the signal is shift to the left, that is advancement in the sequence. So according to this definition we can comment that our second signal is x of n minus 5. So here m is positive, so x of n, which is the original signal in the first plot, is actually delayed or right shifted by 5 units. And if we plot a signal, just for your practice, plot a signal x of n plus 5, and x of n plus 5 is actually x of n advanced by or left shifted by 5 units. The second important and useful manipulation technique of discrete time signal is time reversal. So to reverse the sequence, suppose we have a sequence x of n and we have to reverse that sequence. So we rotate x of n about the vertical axis to obtain the time reversed signal x of minus n. As shown in the figure 2, the first signal is x of n and the second signal is the reversed version of the original signal, which is x of minus n. So what is going here? We are simply replacing n with minus 1. So x of minus n is the time reversed version of x of n. Notice that the origin, that is n is equal to 0, is the anchor point or the center point, which remains unchanged under the time reversal operation. Just as in the case of continuous time signal, the anchor point remains unchanged So in discrete time signals also, the anchor point, which is n is equal to 0, will remain unchanged under this time reversal operation. And also note that, like in continuous signal, the reversal of the signal about the vertical axis is basically signal reversal, and if we reverse the signal along the horizontal axis, we get negative of that signal. So this is also valid for the discrete time signal. If we reverse the signal, or if we rotate the sample or sequence about the vertical axis, suppose x of n is the original sequence, so if we rotate or reverse this sequence about the vertical axis, we will get x of minus n. Original signal is x of n, and after reversal about the vertical axis, we will get x of minus n. But if we reverse the same sequence about the horizontal axis, then we will get minus x of n. Original signal is x of n, and if we reverse about the horizontal axis, we will get minus x of n. So there is a difference how we are reversing a signal, or are we reversing the signal values. So reversal is basically reversal about the vertical axis. I hope that these two manipulation technique is quite clear to you. Now moving towards the third manipulation technique, which is time scaling. The last manipulation technique is basically sampling rate alteration, and here we have two subcategories of this rate alteration. One is known as decimation and the other is interpolation. So this sampling rate alteration is somewhat similar to the time scaling in continuous time signal, which we have discussed in the previous slides. So to understand this concept, consider a signal x of n as shown in the first figure highlighted by the indicator. Please see this figure. This is the first figure and original signal x of n, and we have to compress this signal by a factor m. So compressing this original signal x of n by m factor, it will gives us another signal which is the compressed version of the original signal. You can see the second plot as highlighted by my pointer. This one is the compressed version of this signal. But because there is a restriction that discrete time signals are defined only for integer values, so we are bounded to select integer values of m. We can't take m as 0.1 or 0.2 because m will multiply it by n and it must be an integer value, because here we are dealing with the sequence. So the first sample, second sample or third sample is here, not the 1.1 sample or 1.2 sample. So m must be an integer value. So the value of x of mn at n is equal to 0, 1, 2, 3 are x of 0, x of 1m, x of 2m and x of 3m and so on. So I mean to say that x of mn select every mth sample of x of n and deletes all the samples in between. You can verify this from these two plots also. First one is the original, and if we are compressing this sequence, then the certain values or certain samples are deleted. So because of this very reason, we also call this operation as decimation. It is written on the slide also. This is also known as decimation because it reduces the number of samples by a factor of m. So if x of n, which is original signal, is obtained by sampling of a continuous time signal, so this operation, which is reducing the sampling rate by m factor, so that's why decimation is also known as downsampling. So the first signal is the original signal, second signal is x of nm, and capital M is selected as 2 here, and the second signal is obtained by deleting the odd number of samples of x of n. But if we look it into more detail, then in continuous time signal, time compression speed up the signal without the loss of any data. But if we are talking about the discrete time signals or decimation or downsampling in discrete time signal, so it generally causes loss of data. So under certain conditions, and what are those conditions? For example, if x of n, which is the original signal, is the result of oversampling of some continuous time signal, then the decimated signal or decimated sequence may retain the complete information. Otherwise, if we apply this decimation technique on a usual signal, usual sample or sequence, then we may face loss of data. But on the other hand, if we talk about the expansion of a sequence, then you can see the plot C. We are basically expanding the sequence. So if we are expanding the sequence, it means we are adding samples between the two samples. And how much samples will be added? It depends upon the value of expansion or how much we are expanding the signal. So one thing we may compare between the compressed signal and expanded sequence is this, that the expanded sequence contains all the data of x of n. You can also see from the plots that all values are retained in the expanded sequence, which is the zero valued sample can be reconstructed from non-zero valued samples by using suitable interpolation formula as shown in the plot D. We are retrieving that missing values by using the interpolation technique. So this is the another way to formulate the sequence more accurately, to apply some interpolation technique. Otherwise, in the plot C, we have already expanded the signal. I hope that these three manipulation techniques of discrete time signals are crystal clear to you all people. And for better understanding, I am giving you one task which is in the next slide for your practice. So here is the task. What you have to do, it is just a simple task. I have not added all the three manipulation technique in a single task. We will practice it in the live session. I just gave you a single task. What you have to do, you have to plot a sequence x of n, and in that sequence you have to plot the function e raised to power minus 0.5 n, and the range of n is -3 to 2 and 0 otherwise. you have to just sketch the time reversed signal. Obviously we can apply other manipulation techniques such as scaling or shifting to this signal, but we are limiting the task to the time reversing operation only. So here is the end of lecture number 6. In the live session we will discuss inshallah about the discrete time system properties such as time variance, linearity and other properties. So if you have any queries regarding lecture 4, 5 and 6, you may discuss it with me in the live session. Thank you.